Hi, my name's Peter, and I'm the co-founder and CTO of StarSolar. And StarSolar aims to increase solar efficiencies through photonic crystals. So, what's the status of the solar industry today? It's actually a surprisingly large industry for those of you who haven't been following. $12 billion as of 2006, growing at a torrid rate, 30% or more per year. However, everything comes to an end. And in particular, there are two barriers to further growth in the solar industry. The first is the size of solar panels. They cover such a large area in order to harvest enough energy from the sun that it can actually be unsightly and very expensive to install, which brings me to the next point, which is the cost. Right now, because of the combination of the low efficiencies and high silicon usage, prices are above grid parity, typically anywhere from 25 to 40 cents, depending on the level of subsidies and a number of other factors. Whereas grid prices in Massachusetts would be on the order of 9 cents. There's a couple markets like Japan where you're pretty close to grid parity, but it's not quite there yet. So what do? We reduce the solar cost. And the way that this works is that we use a novel patent-pending technology that was developed at MIT, where I'm a student. And basically what it consists of is a novel light trapping approach. Once you improve the light trapping, that leads to much higher efficiencies on the order of 35% better than you would have had before, and I'll explain that in a minute, how that works. There's two benefits from this big improvement in efficiency. In particular, you get higher power output per panel, so then that reduces the size of the installation for a given power generation capacity. And then the second result is that you get a faster payback for the end user, which should increase consumer acceptance and thus bring solar into the mainstream. So first I'm going to give you a brief overview of how existing technologies work, and then I'm going to go into our technology and why it's different. Basically, existing technology consists of two key components. There's an aluminum back reflector, which is depicted on the bottom of this diagram, and then there's a textured surface on the front. And so what happens is the light comes in, the texturing deflects it a little bit, so it takes a slightly longer path, the aluminum bounces it back, and then it goes out the cell again. So there's a couple of disadvantages. First, there's limited efficacy. You can prove that there's a theoretical maximum, and in practice, real solar cells don't really even come close to that, especially in industrial settings. And then the second problem is electrical losses that are introduced by these features, especially the texturing. So we trap light more efficiently, and the way that we do that is by capturing it with photonic crystals. So what I've illustrated on the bottom is our technology. Basically, it shows that the light comes in, and then what you see on the bottom, that periodic array of holes is a photonic crystal. Basically, it's air holes in silicon, or it could be silica, if that's more mechanically stable. And then it causes the light to be diffracted into this mode, which is not unlike a mode in a fiber optic line, which is internally reflected. So that means that it bounces back and forth, as you see in the diagram going off to the left there. And it has enough time to be fully absorbed by the solar cell, unlike before. So overall, this leads to a 35% efficiency improvement in simulations. And this is also supported by a large body of experiments on photonic crystals. However, the thing that we're doing is applying the photonic crystals to solar cells, and that's what our patent covers. So obviously a key issue is how do you actually make these photonic crystals, because you can't just buy them at your grocery store right now. So what do? We introduce a nanotechnology-based step which comes before the metallization of a solar cell. And it consists of a couple of steps, basically. First, you stamp a sacrificial layer with a master imprint, which is depicted here. And there's a variety of ways to make that. I don't have time to go into that. But then what you do is you transfer that pattern, which you just stamped, into the silicon. And so basically you end up with a silicon photonic crystal. And this enables low-cost, high-volume production of photonic crystals because it's just a stamp and transfer process. That can be done in seconds. So what's our business model? We're going to make and sell photonic crystals that will go on the back of solar cells. This will essentially make us an equipment supplier, not unlike DuPont or Saint-Gobain or many other existing equipment suppliers for solar cells. And our photonic crystals are extremely thin, on the order of microns. So these will look like, basically look like a very thin film to the solar cell manufacturer, and ideally will be flexible film, which they can peel and stick on the back of their solar cells. Another alternative business model that we're keeping ourselves open to is selling the entire machine outright to the solar cell manufacturers, thus becoming an equipment supplier, not unlike GT Solar or Applied Materials or any other number of companies that are supplying large-scale capital equipment and doing quite well for themselves right now. How are we going to go to market? We're building a very small executive sales team that will have strong industry contacts. We already have one team member, Anthony Fotopoulos. I'll go over his background, but let's just say that he knows who these people are and he knows where they live. So, who are we targeting specifically? Thin crystalline silicon manufacturers. So the first one is CSG Solar. CSG Solar is a startup that's building manufacturing capacity right now out of Germany, and it's being funded by Q-Cells. And then there's also Evergreen, who's in our backyard in Marlborough, Massachusetts. And while they don't benefit quite as much from our technology, we would love to work with them, and they could still see some benefit. And then there's other crystalline thin film players in the market who I'm sure would love to have our technology once we prove it. And also, the industry trend towards thinner silicon will actually expand our market. However, don't take that to mean that if the silicon shortage is solved tomorrow, then suddenly it kills our momentum. Our value proposition is in no way dependent on silicon shortage. Let me go over the competitive landscape right now. Traditional light trapping approaches, like I explained previously, are limited in their efficacy, but of course that's what people know, so there'll be some resistance there. There's other nanoscale light trapping approaches. I've seen a couple of them. Some are based on plasmons. They're kind of interesting, but I think there's a lot of work to be done. They aren't really fully understood theoretically, so, and they're not being commercialized. That's the most important point from our point of view right now. Also, we're complementary with many other new solar cell technologies that are coming out into the marketplace. In particular, there's concentrators put out by Stellaris, the winner of last year's Ignite Clean Energy competition. There's cogeneration technology where you use what would otherwise be waste heat to generate additional power, and improved AR coatings, which is something we've thought about as well as other groups. In no ways are they mutually exclusive with what we're doing. In conclusion, few other people are really looking at the back of cells, but that's an increasingly important area to look at. Who's our management team? Well, first of all, there's myself. I'm PhD in physics, completing the PhD in less than a week from now. So I've been studying optical devices for 7 years now, since 2000. There's Anthony Fotopoulos. He's co-author of Solar Annual 2006 with Michael Rogal, who's a well-known industry analyst. And he's worked with Conergy, who's one of the largest solar distributors in the world right now. And obviously, this team is very small, so we need to build it up further, hire a CEO and other management team members who have startup experience. Our sales plan. So I told you we were going to sell a photonic crystal. We've estimated that we can sell it at $35 per square meter. So that'll bring us up to an addressable market of $283 million. With 25% market penetration, we expect that we could have $71 million in annual revenues by year 5. So right now we're in R&D. We filed a patent, as I said, created an optimized solar design, found an industrial partner who's willing to work with us on developing the prototype. And now we want to develop that prototype with $500,000 in funding, hire the CEO and management team, and then next year, once we hit those milestones, then use $3.5 million approximately to develop a manufacturing pilot, which will build the photonic crystals, then provide them to our customers. Thank you.